Hello, everyone, and welcome back to Tech With Shas. Today, we are diving into one of the most fundamental algorithms in machine learning, that is logistic regression. If you have ever wondered how your email knows what is the spam and how bank decides who gets a loan, this is the algorithm behind it. I prepared a simple step-by-step breakdown, so let's get started. What is the exactly this algorithm means? So, simply put, it's a method used for predicting a binary outcome. By binary, we know that means that an outcome that has only two possibilities, like 0 or 1, yes or no, or true or false, right? So, unlike the linear regression which we read in the previous video, which predicts the values, right? So like house prices or some value, right? But logic regression uses something called as the sigmoid function to handle the classification task. Because here what we are doing, we are trying to classify the task, right? So this function which we see on the screen transforms linear output into probability between 0 and 1. So whatever the task you have in hand to classify, right? So you require probability between 0 and 1, and this function helps in that task, right? So this is very easy for us to classify data into distinct categories, right? So now, to make this more concrete and understand with the real classic examples, like for example, first one is the email spam detection. So here, the input might be email content or the sender, right? The model predicts the probability score to decide whether this email is a spam or not a spam. Second use case which you see is the disease diagnosis. Doctors use patient symptoms or test results as input. So the model calculates the risk probability to predict whether the disease is present or not. So that can be probability of 1 or 0. Then the third use case, which is which you can see on your screen, right? That is the loan default prediction. So when you apply for the loan, right? So bank look at the credit score and debt and other many parameters, right? And then the model predicts whether the customer will default or repay the loan in long term, right? So in all these cases, we are dealing with the probabilities to make a decision, right? So here, the decision is binary, whether it's a spam or non-spam, disease or healthy, and the same gives the bank as well, right? So basically, we are dealing with the binary classification cases. Now, let's visualize the problem. Left-hand side, we have a problem where to classify the basically the data, right? So we want to separate the red dots from blue squares, right? A straight line doesn't fit always probability well. So, because this function is not very linear, so we cannot use the straight line. So instead, we use the curve you see on the right. That is the sigmoid function. So it takes any input values and squashes in probability range between u and 1. So basically, whatever the value you are passing to sigmoid function, you get the value between the u and 1, which is the probability of the particular event or task, right? So let's understand the about this function first. Okay, so let's zoom into that curve. This is a part of logistic regression. The sigmoid function, mathematically, we say basically is like a p is equal to 1 upon 1 plus e to power minus z, right? So, but yeah, don't let the math scare you all. All the formula, just is to map any input. So, whatever input you have, you want to classify whether it's a true or false, whatever the case may be, right? So, no matter how large or small value, you want to basically stick value into 0 and 1, right? Range, right? So that's why we use this sigmoid function for the whenever we want to use the binary classification, because any value, whatever value you get as an input, when you put in this formula, you get the value between 0 to 1. So suppose the probability is near 0, you can say it is a false. If probability is near to 1, you can say it is true. Okay. So as the input grows larger, the probability gets closer to 1. As it goes lower, it goes closer to 0, right? So the S shape, right, which you see here in this graph, is crucial for accurate classification. Okay. So just remember this function is used for the binary classification. Nothing to be scared of. Okay. So now let's see. So how does the model actually process data, right? So I mean there are three steps. So first is the we have to have the linear combination of data, right? So first we calculate a weighted sum of our inputs. So you can see here the z is equal to, we have this w1 x1 w2 x2, right? Summation of all these weights and their features, right? So all these x, right, x1 x2 are features. So for any case you want to solve, right, and classify it, you will have, right, some features to identify the features, right? So like that. So here first step is to calculate a weighted sum of our inputs, that is the features and biases, and this look like a simple equation of a line, right? So next step is the sigmoid function, which we have seen in the previous slide. So when you feed this z, right, in that sigmoid function formula, you get a value basically transform between 0 and 1. So if now you got the value, right, so value is greater than or equal to zero point 0.5, you can say predict class 1, for example, spam, right? If the probability is less than zero point 0.5, you can say the class 0 or not spam. So basically, first step is to find the features of particular use case, and then have some bias value as well, and finally the combination of the this combination of the state line. Then the value, whatever you see here, right, the weighted sum, we put into the sigmoid function, and then from there we find out the value of the probability. If probability is greater than or equal to zero point 0.5, we say it's a true. Average less than 0.5, we say the false, right? So this is how we can classify our the data, right? But now the question is that how does the model know the correct weights, W's and biases B? So basically it has to learn them. This process has three stages as you see on the screen. First stage is the AC parameters. So we start with random weights, like we have multiple W's and bias, right? So we assign random values to them, and then once you predict, you can see on the left hand side that the model initially makes very poor predictions. The model is not able to properly predict the correct output because whatever the weights we have chosen, they are random. Then second stage is the cost function and gradient descent. So we measure the error using a cost function. So we have our actual labels from the test data. We also got the predicted label, right? So based on that, we find out the cost or loss, right? What is the loss happening? So and the focus of this GD or the gate algorithm is that to minimize the loss. That's why you can see it is a kind of a convex curve, right? Because in the convex curve, you find out the lowest point. And just think is as a wall rolling down a hill to find lowest point. So ultimately, we initialize our parameters randomly, and then we predict the values. And once we compare from the actual the expected output and with the cost function and apply this gradient descent algorithm, we want to minimize this loss. Okay, so once we minimize this loss and what happened, right? So we keep doing it multiple times. Okay, so we update the weights multiple times, and we repeat this until we find the best fit or best parameters which are very accurate in terms of prediction. So then the model updates its parameters to minimize error, resulting in the accurate separation of data you see on right. So initially the data was not properly separable, but here after we found out the correct weights and bias, by the multiple iterations of the minimizing the cost function loss. So we found the proper best fit. Now you might ask that can't we use the same error formula or cost formula as we use in the linear regression? So the answer is no, because in linear regression we use squared error, but if we use it that in this also, the cost function become non-convex, because here we want a convex function, because if you have a convex function, it is easy to find the minimum point, right? So instead we use log loss or cross entropy. Looking at the graph on right hand side, if the actual value is 1, that is y equal to 1, the cost is huge. If predict 0, okay. So this formula heavily penalizes confident wrong predictions, creating a smooth convex curve that ensures we can find the best parameters easily. Okay. So for each wrong prediction, it is penalizing heavy so that we are able to find out the best fit parameters. Now you can see the detailed formula of the log loss. So I won't go into this formula, but if we break down this intuitively, so if the actual label is 1, for example, you have some data and you classify it as a label as a 1. So we only look at the first part of the term. If a prediction is close to 1 or cost is 0. So if we are predicting properly, correctly, then there is no cost or very less cost, right? But if we predict 0, the cost goes to infinity. So it is how this able to penalize the wrong predictions, right? So in second level, I mean the actual label is 0. So we can look at the second part, right? So if we predict 0, cost is 0. So what I mean, if the actual label vector level is same, cost is low. But if it is not correct, then there's a heavy penalty because sky, because whatever the cost, right, it get skyrockets. Okay, so this ensures that model learns to avoid the hallucination. I mean, how it can avoid the mistakes which are done with very confidence, right? So basically, focus is that model should be able to avoid mistakes which are not good in terms of because they will be giving a very high loss because of these common mistakes. Now, once we have understood the cost function, right? So, like once we decide, okay, what is our cost function, we use the gradient descent to minimize it. Here, the goal is to iteratively update our weights, like I mentioned earlier also, that we initially take the random weights and biases, then we start iterating to find the global minimum of the cost function. So the cost function which we have seen earlier, we try to find out the minimum value for that, and in this manner, what we do, we use the update rule. That is the theta new is equal to theta old and minus alpha into delta j theta, right? So alpha is learning rate, so step size. So how fast or how slow you want to iterate over the multiple iterations, right? That's what alpha. Okay, so we calculate the gradient or derivative to determine the direction of the steepest descent. Visually on the convex surface, we are stepping down towards the center, right? So that is our goal. So if we start using the initial weights as random weights and then minimize the cost function loss, then ultimately we update it and then find the lowest point in the converse curve where we have the minimum cost, right? So this is how we are getting the actual correct parameters. Now, the main question is that once we have our model trained, okay, you have done multiple iterations and found out the all the required weights and biases. So how to evaluate it, right? So because evaluating model is really important. So we have several metrics for that. First is the conversion metrics. So conversion metrics comprises our predicted labels against the actual labels shows as true, positive, false, positive, etc. Then we have other matrices like accuracy, precision, recall, and F1 score. I mean, precision and recall on this conversion matrix is very important aspect in the machine learning for the evaluation. So maybe I can create a separate video for that if there is a requirement. Okay. Another way to basically find out the performance of the model is the ROC and AUC. We also use the ROC curve. The AUC area under curve tells us how well our model distinguishes between the classes. So how well it is able to distinguish between the I mean the wrong and the correct predictions. And then there is just like these formulas are there like accuracy, precision, but apart from this formula, there is a lot behind it, like in which scenarios we have to use accuracy, in which scenarios we have to use recall or precision. There is a different use case altogether. So understand is important. So yeah, so and that's it. In nutshell, this is the logic regression. I hope this slide by slide breakdown helped clarify how we move from linear input to probability-based decisions. If you found this video helpful, please hit the like button and share it with your friends. And don't forget to subscribe to Tech with Shas for more simplified and tech concepts across the system design and machine learning. And thanks for watching, and I will see you in the next video. Thank you very much.